used to be more excited.
It leaves me lots of times slowing down and necessary. Can't pull it down, but it's kind of interesting because my close-up depth is 7 meters 5 and my distant depth is 7 meters 7. If I'm working with small parts of 7 meters circuit board, I think they are. It's obvious. This I didn't know why it was all they want to be quite my drivers like this. They drive down around the airplanes. You're supposed to get in the same piece of 20 feet away. Those people that do it all those kids, I got out there, I killed them. If I don't be a instructor going forward, drivers, I'm trying to go back to that. Second class. Yeah, sidewalk. Story. Everybody else. So now there's no witnesses being the instructor. And then you got to kind of like that. There's not the clear time I ran the chance I got the instructor. Okay, be careful. Together. That's it. I wish somebody would say something because I'm already got the body of the primary, got windows, that room has no reference to the ground. So you can't tell what it is except by temperature. So that's why you put the test in. But anyway, the test serves its purpose and make you very cautious. Yeah, I would make a mess of that.
Yeah, I have one. It only goes 40 miles an hour. But I have one that would go 70. No, I have it, but I don't have a battery. Those are lipo. You have to have a lipo battery. And it's like, I don't know what happened. It's like exploded inside of its plastic case. So it was all like swelled up. I was like, I don't want to touch that anymore. And I put it in the fireproof bag.
Was that a lithium battery?
Polymer, lithium.
Yeah, they catch fire.
Yeah, I didn't. They do.
Apparently they were very much put out.
If you watch that drone, you ever watch Drone Racing League? It's on ESPN, and one of the guys there was telling the story. He was charging one of his, and it burned his apartment down. He tried to save stuff and throw stuff out the window, and he said he got burned.
It's not like you can throw a bunch of lithium in a bucket of water.
I stick to that NICAD.
Open on both sides. So each of them was there, the other could fly the plane. The other guy could the other guy fly the air. It's flew through there, and this guy comes out on the other side and goes up, all is well, right after the plane went through. Sometimes because you know how the engine sounds. That was before they put my voice on. So this thing goes screaming through the car. The world was yeah, they don't have any dollars to change how he gets over that fly through the railroad car. This is getting worse after they fly in the place long.
So in your
But at least you know. You have to make the simulation more realistic. That's the things that crash into your legs and crash and make it all. But that should be Rock Hill, South Carolina. How far from here? I know. Maybe instead of having. I think I'm more every 2 day drive for the old country like that. I should run through this and my drive to our friend's house in Virginia. This is a 5-hour drive.
Well, our penultimate presentation today is from Dr. Chuck Higgins, Radio Joe Citizen Science for the 2017 solar eclipse. Thank you.
Thank you, Tom. Thank you all. I apologize that I did not get my paper in on time, so it's not in the proceedings, but I will make it available on a CD or perhaps put it in the next SARA Journal or something. So, Radio Joe, you know us very well. We have a great collaboration with SARA. We definitely love that. And the solar eclipse this year has got us all excited. So I just wanted to give you a quick update of what we're going to be doing. And hopefully we'll be back next year and we'll tell you what we found. So we are collaborating with a guy at NASA, Goddard, Sheng Feng, and we have a grant, education grant. So this work really is part of an education grant. And so it's Jim Tiemann, who you know from Radio Joe, and Leonard Garcia from Radio Joe, and myself. And this awesome group of observers, many of you have done great observations for us. We thank you. And we have, we're recruiting more observers for our solar eclipse event. So I won't bore you with this too much, but so you know Radio Joe is an education project started in '99 to really get people interested in radio astronomy and science. And so we're still operating, we are still selling kits, and we've sold over 2,200 of them. So they're out there, I don't know where they are. They're out there. So we try to, keep in touch with as many people as possible, obviously, but it's an introductory project, an education project, but we are widening our breadth to get involved in more science projects. So that's something that we've been actively trying to do. And so our basic kit, is a simple receiver, single or double dipole, and awesome software from Jim Sky, as many of you know. So that's a great tool for us for not only taking data, analyzing data, but connecting with other folks, real time through the web. In the last few years, we've had some super Radio Jove users, so broaden our bandwidth as well. So we went from single frequency, essentially at 20.1, to 15 megahertz bandwidth with Dick Flagg's sweeping spectrographs. And now we've got 7 or 8 of these around the country that can observe not only wide bandwidth, but dual polarization. So we're using wideband antennas and these spectrographs to get some now scientific quality data. So you can see a couple of examples here of some. So this is frequency and time, and then the intensity, of course, is in the color bars. But type 3 solar burst. 20.1 megahertz would just be a single line on here, so it would look like something like this on the strip chart. And you can get some spectral detail and learn something more about what's going on across the spectrum. And of course, we started the project because we all love Jupiter. And you can observe Jupiter. So now at wide bandwidth, you can not only get polarization information, it tells you something about the emission, where it's coming from. You get some incredible spectral detail, Faraday bands, and other structure that is unique to Jupiter. So this is really, Jim Brown, as all of you know Jim, but he's got an antenna farm now in his backyard, so he's been doing a lot of data collecting and hardware testing, antenna testing. So we're really making some great leaps forward, not only in, and then I should mention Jim Sky again with the software. So he has free spectrograph software that allows you to make these fantastic displays. So this partnership it's a very, very large grant, Heliospheric Education Consortium, and Radio Jove is just one small part of this. And if all goes well, it's a 5-year grant, and we'll be able to set up, what we're trying to do is set up observing stations, spectrograph observing stations around the country, or not limited to this country, but the funding probably is. Set up spectrograph stations to do sort of a longer-term study of the Sun, Jupiter, Earth's ionosphere. Now we roll it into the education as well, but we're trying to do some science with it. So you can see we are going to be, and we're using the solar eclipse as our rallying cry here, the near-term rallying cry to get people educated, citizen scientists involved, to try to sort of up our game, and as opposed to just being an education tool. We want to be a science tool as well. So Jupiter, as always, And so that's what I studied Jupiter's radio emissions. So the solar science and certainly the ionospheric science is newish to me, but this is it's going to be a fun, hopefully a fun project. So we are again looking at Jupiter, the Sun, and perhaps the solar wind, and Earth's ionosphere. So we're going to study the propagation of galactic background, signals, bursts, radio bursts from the Sun, radio bursts from Jupiter, and how it propagates not only through the ionosphere, but through the solar wind. And perhaps just try to understand the densities, the ionization, the ionosphere over time. Maybe if the CME goes off, we'll get lucky and get the right configuration to study these things. So, as I said, it's a few years that we're going to be able to study this and hopefully get a worldwide team to help us take data. But specifically for the solar eclipse, we have about 25 observers who have agreed to take data for us for the solar eclipse. And I think I can count 2 more since talking to a couple of you this week. So that's great. We welcome that. We're spread around the country, and Bob, where are you? It didn't occur to me that the shadow zone for the ionosphere is not going to be the same shadow zone optically, but that's okay. It'll be a wider shadow zone. But we're interested in what the ionosphere is going to do, as you've heard a couple of other folks talk about already, what the ionosphere is going to do during the solar eclipse. And we're at 20 megahertz, and to my knowledge, that's not been done. But here's our team so far. The red stars there indicate where we're located, and we're trying to get small groups of spectrograph observers to be located geographically close to one another, and use that as sort of a point where we can maybe expand and get a group of 4 or 5 people in one area and do this around the country. Because, as you've heard other people say today, and I will maybe summarize, the ionosphere is one interesting character and very, very dynamic. I mean, it's unpredictable what this thing is doing. And especially during a solar eclipse, you know, there's certainly been studies of what happens, but it's a beast to try to understand what the ionosphere is doing. And I don't have the answers either, but this is perhaps another way of studying it. And so if we get many perspectives, of course we'll have people in the partial eclipse zone and people in the total eclipse zone, and if we're all gathering data that's calibrated, and hopefully we might be able to detect some changes during the solar eclipse. That's the goal. So we see several stations. We've been observing spectrographs. So here's our station, one in Florida, and Jim Brown. That should be Industry, PA, right? Yeah. Yeah, sorry about that. I don't know how that turned into factory. Pretty close. So, very interesting type 3 burst. You see it has a kind of a low end in terms of the cutoff of the frequency. So why is that? And so that's something we can look at. If you have simultaneous observations of several stations distributed latitudinally in time, then you might be able to address what's happening perhaps locally in the ionosphere. And we know that during solar events you get massive ionospheric disturbances, and that affects communications. You see blackouts, fade outs. So in some cases, you know, we can trace these back to the event, the flare that happens on the sun. So you guys know this, but this is with multiple people observing. We hope to learn something more about what's happening there. And I did not line this one up in time here, but this is all the same verse. Jim has a single frequency and a spectrograph running, and then I had my spectrograph running, so we're seeing the same type 3 event. And what is that going to do to the ionosphere? So is that something that we can measure the ionospheric densities? Can we measure changes using the SID program? I think that's going to be a great study. I think this Eclipse MOB project is going to be a fantastic way to study the ionosphere during the solar eclipse. So this is just a different aspect to it. Yeah?
Looks like Jim's using the EDRR antenna on that top.
It works.
Does it say that?
You had to be there.
No, that's the FSX. But what's the antenna you got to never see? LWA. Yeah, he's got a good antenna on that one. So we're going to do it a slightly different way. So we are going to look at the galactic background. So we can study the density of the solar wind if we can get lucky and get Jupiter, if it's near the sun, and get a strong Jupiter event propagates through a coronal ejection or something, that we might be able to kind of work backwards and study how that solar wind is changing. 20 megahertz is basically above the ionosphere cutoff. We observe typically at night for Jupiter just because it's less absorption. But with the spectrographs, we can go down to 15, and if we retune it, we could probably go down a couple more megahertz. But we're right on that edge, and so most of the absorption for us is happening in the D layer. And so that's different from the other studies that are looking at the F layer. So what we're going to do is, well, let me just say, so you've seen this before, that the solar eclipses do affect the ionosphere. So this is just another paper showing the effects again of the '99 eclipse over Europe, showing the cutoff, F2 communication cutoff frequency during the eclipse here on August 11th, and then August 10th, August 12th, those are non-eclipse days data. So you can see the cutoff frequency directly affected by the solar eclipse. So the question is, are we going to see anything happening in the D layer? Are we going to be able to detect the absorption or lack of absorption during the total eclipse? So here's what we're doing. And we've never done this before, so we're not sure what our results are going to be. I'm not going to be as brave as Rich here and predict what's going to happen. So I'm going to tell you what we're going to try, and we're hopeful we'll get some results. So I steal a lot of data from Jim. So here is a 24-hour 20.1 megahertz showing at the bottom there, that's a galactic background. So I've switched this into sidereal time, but here is the background temperature, so it's calibrated. At 20 megahertz, we should be somewhere between 40 and 60 K. And you can clearly see background hump of the galaxy. So you're seeing the galaxy crossing the planet slowly. So that's the Milky Way. Do you see the other hump on this graph? You see the anti-center. So that's the galactic center. 12 hours later, you see the anti-center. So if you've got a good quiet sight, you can actually see both transits of the Milky Way at 20 megahertz. So what we have to do, and sometimes things don't go well, and you have days that are good and days that are bad. Sorry, Jim, again, I'm not picking on you, but you had some really nice data out there. So here's a good day. Lots of perhaps distant lightning here during the daytime hours. But even during the daytime hours, you can see that galactic hump. Not a problem. Sometimes things happen. Yes, power lines. Things happen. So, we're going to have to be careful about what data we include. What we're trying to do is basically statistics here. We want to gather day after day after day of galactic background levels at all local times. And you build up those data and you create what's called a quiet day curve. So this is one that was done in 1980 at 30 megahertz. So this is voltage, but you can do dB, or you can, in our case, we'll do antenna temperature as a function of sidereal time. So we're doing sidereal time because we need to know where the galaxy is. And the galaxy is always going to be at the same spot, sidereally. So we need to painstakingly make these quiet day curves so we have a baseline of what the galactic background will be at 20 megahertz for that specific time, local time bin. Sidereal time bin at that place. So Jim has been taking data for 100 years now, Jim? Something like that? Gosh, going on 18 years, 17 or 18 years. We've got several folks in Florida that are dedicated to observing for many, many years. I've got several years of data. So we can, again, this is going to take some time to do this, but we'll make this quiet day curve, and we will compare the data for August 21st at, I think the eclipse runs from about 9:30 to 12 or 12:30 sidereal time. This is in Murfreesboro, where I am. Anyway, so we will look at the day of the eclipse, and we can then compare it to what we should have gotten without an eclipse. Right? So that's the idea. So we're looking at the galaxy always emitting, right? The galaxy is always emitting. Now it will be absorbed somewhat by the ionosphere. But what happens when you have an eclipse? You'll get more galaxy, right? The ionosphere cools off, and it's less absorptive, maybe during that 3 hours. So instead of a signal drop-off, we should see a slight elevation in signal compared to a quiet day. All right? That's the idea. And so you have to, again, take the data, bin them in sidereal time, and bin them in temperature, antenna temperature, and then you remove the spikes. You remove all the interference, and you do that. This technique from Armstrong, you pick what we call the inflection point. So anything to the right, the strongest signals, you're going to reject those. So it's just a way to be systematic about how you remove the interference. So This is the change in electron density as a function of time during eclipse. But of course, we're not going to see that, right? We're going to see, hopefully, an increase during the eclipse because the ionosphere is less absorptive during the 3 hours during the eclipse. I don't know if we'll see anything. And we may not know until we crunch a lot more data and get a very nice quiet day curve at several different sites to be able to say whether we're going to get, or whether we detected a change due to the eclipse or not. The other thing that we will be doing, so we'll be observing, we have the whole team that's going to be observing, is, there's a tiny chance we might get really lucky and the sun might be active that day. The sun's been pretty quiet, as many of you know here, pretty really recently, but there was a sunspot a few weeks ago that rolled around and it was very active. So imagine what might happen if you've got an active spot on the sun. Then you've got maybe the moon covering it for some folks, or you might get some attenuation of that solar burst. Some groups, part of the country might pick it up, others might not. We might be able to triangulate where that source is, if there's perhaps multiple sources. So that's a very long shot, but that's something that we're going to do and be looking for, obviously, as well. All right, that's it. Thank you so much. I just want to give you this brief update of what our plans are for the eclipse, and tell you that we're still out here, and we'd love to have more partners with us. I am the kit distributor, so if you are interested in ordering a kit or getting involved, you can certainly, there's brochures out there on the table. Thanks, Bill, for putting them out. You can catch me after this evening. I'll be around, and I'm happy to answer any questions. So I appreciate your attention. Thank you.
What's the pricing for the kits?
So the kits now are $210, and that's essentially cost. We order the parts in bulk and try to keep the cost down as much as possible.
So what's in the box?
What's in the box? Let me go back to the screen where I show you the kit setup. There. Nope. There. We get all the parts for the receiver, and you have to build it. That's the fun part, right? So everything for the receiver, you get connectors and coax and wire for your antenna. And you get the software. And you get the instruction manuals to build everything. But the instruction manuals and GIM software, the free version of GIM software, many of you know, is online. You can download the free version. The only thing you don't get in the kit are the ropes and the poles to mount your back poles. Everything else is there. The calibrator, so we do offer a calibrator. Again, that was something Dick Flagg wanted to do to improve our capabilities, scientific capabilities. So the calibrator is another $100, but it's not absolutely required because you can do relative measurements. You can still observe the sun and Jupiter. You just don't know what your absolute scale is. So that's the essence of the kit.
So what type of receiver is that?
What's in the box?
What's in the box? So it is a PC board. You've got the enclosure and all the parts and bags and an instruction manual. And it's essentially a direct conversion receiver.
It's essentially a CW SSB receiver.
Yeah.
20 megahertz.
It's centered at 20.1. You tune it. Yeah, there's a 20 megahertz oscillator in there, and you tune it up.
And what does it output?
It outputs audio.
Two ports.
Two audio outputs. And the beauty of the Radio Sky 5 software is you take that audio signal into your computer and it digitizes it.
So any HF receiver will do this.
Any HF receiver
Now,
will do it. Two things, single sideband is optimal, and then it's got to have the AGC switch turned off. Otherwise, you won't ever hear Jupiter.
390 does it.
A what?
If you don't know, it won't be.
Oh, okay.
But a lot of people here will know.
Say R390?
Yes.
With,
R390 Alpha.
you talked about a Spectrum one. Is that a new kit that's going to come out then?
Good question. So the we have sweeping spectrographs that, again, these are Dick Flag designed and built machines. You can order one through him, but that is not going to be a kit, no.
Okay.
At the moment, we have, as Jim is doing this too with a couple of other folks, we're testing the SDRs as well, and those may be a cheaper and better way to go long term. Yeah, so we're in the process of writing up some manuals and trying to get some instructions so other folks can have these kinds of things. So, but you still need a wideband antenna. You know, a dipole will get you a couple megahertz, but if you want to get 10 or 15 megahertz, you'll have to get a wideband antenna. Do you have a question?
It was the same question, whether the spectrograph would be for sale.
You'd have to communicate with Dick Flag personally on that. He may build you one, he may not. We've got him pretty tied up with this, the Eclipse for the moment, but long term, I don't know if he's going to build any more of those or not. Yeah.
With SDR, with the RTL SDR, the cheapest dongle you can find from Amazon.
Yeah.
Generally, you have a wide bandwidth, but the lowest frequency is 24 megahertz. Do you think that using that, 24 megahertz, as opposed to 20, 21, would be that choice?
So what's the bandwidth on those?
Oh, the bandwidth
Is big.
So this is between 24 to 2 gigahertz.
Okay, so low end is
But
24.
the sampling is fast enough
Yeah.
to get, I don't know, maybe 4 or 5 megahertz.
It's about 3.
3 megahertz.
Yeah, 24 would be fine for the sun. That's no problem. And Jupiter is a broadband emitter as well. The problem there is that Jupiter above 24, the probability and the intensity of those emissions goes way down. So between the peaks at 8 megahertz, Jupiter does in the spectrum, but we observe 15 to 25 is optimal for Jupiter. And we are recommending, at least right now, we're recommending the SDR Play. That seems to give us the best, and I haven't used one myself, but my trusted student back there, that's going to be John, that's John Jackson. He's first time SARA now member, and he's going to be working on the SDR Play and getting one set up for us. And I forgot to mention that I have, if you don't have one already, please take one, but I have solar eclipse glasses that we'll pass out to everybody here, courtesy of NASA and the Heliospheric Education Consortium. So if you don't have a pair of the solar eclipse glasses, please take one. And John, will you just pass them around?
I was going to toss out on the cheap to use the RTL SDRs. Grab one of the block converters that do almost DC to 30 megahertz. And
yeah. So again, I'm not an expert on the SDRs by any means, but my understanding is those things will saturate very, very easily. The dynamic range is limited, and so we're having better luck, at least with the SDR plays. I mean, they're still only a couple $100, but the performance seems to be pretty pretty incredible.
Isn't it version 2 now?
Version 2, so I didn't get into this, but so if you've got the right kind of antenna, you can do dual polarization. So we set up a square array so we can get left and right circularly polarized, so that helps us detect Jupiter. It's basically circular polarization. So we like the 2-channel, the SDR Play 2, because we can get both left and right output. But SDR Play 1 would be perfectly fine as well. Any other?
Yeah,
Just a quick note, if you use if you use your antennas for ham radio use or something else, keep in mind the Jove receiver and all the antennas are keyed around F connectors, and it's not a bad thing. It's good, it's fine, but it's not bad to keep a couple of converters on hand to go to PL259 or whatever you want.
Right. We don't like the F connectors much either, but they are
It's within the
easy. Yeah, they're easy, and you don't need special equipment to put a connector on some coax. That's sort of as a
I mean,
trade-off.
if you're going to use the calibrator, you want to use it with some other antenna system, you're going to need to have
Yeah.
no big deal.
Right.
By this time, surely quite a lot of data has been collected about Jupiter. Have any conclusions been reached or any hypotheses proposed as a result of these studies?
From the Jupiter studies?
Yes.
Well, yes, lots of things, but that would probably take take you too long to go through a lot of those things. But of course, the magnetic field of Jupiter was proven using radio astronomy. So it was theorized that there was a magnetic field of Jupiter, but it was not known until the radio emissions were discovered in '55. So that gives you evidence of the magnetic field, the components of the magnetic field. You can study the plasma conditions in Jupiter's magnetosphere. You get the rotation rate of Jupiter, which is internal, through radio studies. Now with the Juno mission, the Juno orbiter, that's really a game changer, because now that's a polar orbiter, and that spacecraft is flying right over the auroral zones. Of course, the auroral emissions directly tied with radio emissions. So you've got charged particle interactions with the magnetic field, and those same charged particles called aurora are also causing radio emissions. You have the Io effect as well, but so that spacecraft is going right over the poles of Jupiter and having a look at the emissions, radio and otherwise, UV and other things that we'll never be able to get here on the Earth. So that's really the papers are really just coming out on the Juno mission. And there's going to be a lot of them, I'm sure, because that's as I said, that's a being so close and having that type of orbit is really going to change the understanding of what's happening in Jupiter. Any others? All right, thank you very much. Appreciate it. Hi. You want to plug in here?
So this is our open mic hour. For our first speaker, we have Ellie. Ellie White. And I'll let her describe her project here that she worked on.
Is that you?
Thank you, Ellie, for coming.
Oh, thank you for having me.
Yeah, it's always a privilege to have students here. We love you.
Thank you. So hi, my name is Ellie White. I'll be a senior this year. I'm from Huntington, West Virginia. This is actually the first amateur radio astronomy project I've done, and I know that probably a lot of you have made a similar project, maybe on Super State or something like that. So a lot of this will probably be like old news for you guys, but I'd just like to sort of go over my process here, and just sort of describe the steps I've taken, the experience I had with it. Okay, so first of all, why did I want to build this thing? First of all, it seemed like a good way to get involved in amateur radio astronomy. I had not done any projects to that point, and I was looking for a way to start. So I got the inspiration from a really good book by a guy called Jeff Lashley, which sort of described this project, how it worked. It was also an opportunity to get to know the new radio software, which I wanted to get more familiar with after working with it the summer before. And also, I wanted to contribute to a new project called Open Source Radio Telescopes, which I'll describe further in just a few slides down. It's really interesting. I really look forward to telling you about it. But probably most of all, I wanted to learn more about instrumentation and radio astronomy, because I'm working on a few projects here at Green Bank. I discovered that I'm really interested in that. So I wanted to get more involved and learn more. So the point of the antenna is, of course, to detect solar activity or any other kind of ionospheric activity. And this is sort of like elementary. You guys already all know this stuff, but so of course, extrasolar activity like solar flares increases the ionization in the ionosphere, which causes the VLF waves from VLF station. In my case, I chose to focus on the Cutler Main 24.6 kilohertz station. So, of course, bouncing off the B layer makes the signal have to travel less distance, so it's stronger. So we can detect the signal that way. So I'll just kind of describe my process here. So, of course, we have the antenna, which is pictured on the first slide. That's just a giant loop. And then actually had a tuning amplifying circuit that was built by engineer here, Steve White. And then I, of course, had to upconvert the signal because 24 kilohertz is out of the range of the SDR dongle I used, which is, so upconverter was actually an upconverter, which was not really supposed to work reliably down to 24 kilohertz, but I found that it did. So if any of you have any use for that information. So, so from the dongle, of course, I used a GNU radio flow graph to process the data, and then I wrote a secondary Python program to plot the data. Of course, the final product that we wanted was a data graph showing the signal over time. So the physical construction of the antenna was pretty simple, and this is a pretty sparse slide. So I just built a cross string out of what I found in my backyard, basically. So I wound the antenna with 125 turns over 24 average wire gauge magnet wire, which is really hard to find actually, as I'm sure you know. But so then of course I mounted the antenna to the baseboard using L brackets. So from the antenna, so of course, so I didn't even know this was a step until I started corresponding with Steve White, who requested about this project, and they told me that I need to tune and amplify the signal from the circuit in order for it to show up in my graphs. So, so Steve White built the tuning amplifying circuit, and we actually spent some time here at Green Bank testing it and making sure that everything worked well. So of course we tuned it to 24 kilohertz, so it would be optimized on the Cutler Main signal, and we used the opamps to amplify the signal. in the process of testing, so using and testing this antenna, I came across a couple different softwares, and so I wasn't sure which one to use at first. I started out with SDR Sharp because it's really pretty easy. There's almost no learning curve. You just kind of plug it in and it works. But the problem I was having with SDR Sharp is that it's not easy to see what's going on behind the scenes, and not quite as easy to manipulate by a beginning user like me. So that was one con, and also I couldn't figure out how to make it record data such that it wouldn't completely fill up everything on my computer. So I also sort of looked at GNU Radio. Of course, it's a little bit, the learning curve is a little bit steeper, but it lets you see all the steps that are going on, and lets you easily manipulate them. And it also allows you to record for a really long time without collecting a huge data file. So the results of those comparisons were that I ended up using SDR Sharp to test the antenna initially, and then GNU Radio to do the actual processing. And of course, this analysis was not, I probably didn't get to learn enough about SDR Sharp because I really wanted to use GNU Radio to begin with. So that's that. It could be that there are ways to get SDR Sharp to record a lot of data that I just didn't find out because...
You got the right way.
What model SDR radio are you using? What brain?
SDR, so I'm using Newelec, RTL,
RTL, SDR?
Yeah, I can't remember
The silver
exact
one?
model number. It's the black one, it's
Oh, okay.
the $20 one, so, yeah.
Make sure you talk to me after you do that.
Yeah, and I should have brought the dongle with me so I could read off the model number, but I just, so sorry. So after determining that yes, I was going to use GNU Radio like I thought it was, I built the design flow graph, built it. I used the SDR dongle as an input source, set sampling rate to 2 million samples per second. Performed at 8,992 FFT to achieve a spectral resolution of 244 hertz, which ideally it should be narrower. I eventually moved to 10,000 point FFT, but for the data that I'm going to show here, I used that one that had a spectral resolution of 244 hertz. So then, of course, I squared the complex FFT output and then integrated the signal every 10,000 samples to reduce the amount of data. And then, of course, I saved the output to the file sync and displayed it using a waterfall sync. So I'll show that flow graph here. So you can see first a lot of the people here use GNU Radio, or just some? Yeah, okay. So you guys probably pretty much know what's going on here. So of course, just the source and the FFT block, and then square it, and then integrate the entire file sync and the waterfall sync. So so that was a really interesting learning process. I've actually been sort of tinkering with GNU Radio for about a year now, and I still feel like I'm only at the tip of the iceberg.
So you had no trouble controlling the SDR RTL with GNU?
Right. Yeah, it was actually pretty. That was not really hard at all. The further processing steps were a little like I wasn't fully. I didn't know very much about the digital signal processing aspect until I started talking with Steve and Richard here about it. So that was probably the biggest part of the learning curve for me, and that was really interesting to learn more about. So anyway, so after all those steps, went through all those steps, I came this data set. It's a 24-hour set between July 17th and July 18th. By the way, I've only had this thing fully working for like a week or two now, so I haven't taken a whole lot of data. So I was looking for, of course, the sunrise or sunset signatures to make sure that what I was picking up at 24 kilohertz was not some sort of freaky interference, and it was indeed the variable frequency station. And what I found was that at about 3 o'clock universal time and 10:30 universal time, I did see what resembled sunrise sunset signatures, and they sort of correlated to, see if I have the slide here. So it's sort of, the spacing between those sort of correlated to these. So I figured that I'm definitely thinking of a variable frequency station here. So that was really exciting. Of course, so before I say anything else, we can move to this next slide. So, from this I have some exciting results, but also quite a few questions left. So I'm pretty sure that I've confirmed that the variable frequency station is in fact visible at 24 kilohertz, due to the fact that it, from my studying data, it looks like it has sunrise and sunset signatures. But something I don't understand is that there appear to be some weird large spikes in the data, which I don't see in any of the Stanford data. And so I don't know what's causing that. And in addition to that, you can see that it's quite a bit noisier than in the Stanford data. So I don't know if that's due to like a bandwidth issue or noise from the amplifier, or maybe the Q factor's too low, or
Did you have any problem with the frequency instability of the SDR with respect to staying on the actual transmitter frequency?
That's a good question. So an interesting effect that I've noticed from day-to-day reporting is that the local oscillator seems to. So I think I left this part out. I used a Hammond up converter to up convert the signal, and the signal was at 125 megahertz. And the offset from 125 megahertz, its supposed frequency, and its actual frequency tends to change from day to day. So I think maybe that's something to do with what you're saying there.
And you may want to find that you want to search that FFT after you square it for where the real peak is.
Yeah, and then subtract.
And then say that date.
Yeah. That's fantastic. I actually don't remember to do that. I look for trends.
A digital automatic frequency
Yeah.
controlling effect.
Yeah. Okay, great. Thanks for bringing that up. So of course we have that sort of noise issue, and then so the final thing that I noticed, and this is sort of unrelated to the 24 kilohertz station, is at home I picked up this really strong intermittent signal of about 45 kilohertz. I haven't had it up and running here, so I can't test it yet. But I don't know if that signal is interference or a transmitter. So that's something I need to do some further testing on to see if I can figure it out.
Do you have any dimmer switches in your house that are in use?
That's definitely possible. We have some fans running, yeah.
Dimmer switches will wreak havoc on the system.
Okay, and the way it's switched on and off, I mean, that could also be a transmitter, but that's interesting.
Electronic ballast for LED lights and for fluorescent lights sometimes make noise in that frequency range also.
Oh, okay. And in fact, I think I have those like right next to my antenna setup. So.
Yeah, it may be one of these things that if you watch your receiver output and try turning off all the lights around the house, you may see you turn off a light and all of a sudden the noise level goes way down, and yet that's the bad guy.
Okay, cool.
Turn the whole house off.
To the family, you just have to be in the dark for a few hours while I'm making this observation.
So this is really funny because I actually noticed that dip at about sunset, and I thought it was a sunset signal in the 45 kilohertz channel, but what happened, I bet, is that I just turned on the light. So I saw that decrease in the signal. And
Do some experiments with those light switches and just see if they're your bad guys. Might be.
Yeah, great. Okay, so what did I want to do with this data once I had it? And So the Open Source Radio Telescopes Project, or OSRT, is a new project started up by someone who works here, Dr. Richard Prestige. And the goal of the project is to increase the availability of open source radio telescope plans, documentation, and software. So for educators and students to have better access to. So right now it consists of a website, opensourceradiotelescopes.org, and which has an associated wiki page. And we hope to use that as a home for plans, documentation, and software-defined radio downloads, software downloads. As the project moves further, it's sort of its beginning phases right now, but we have a couple of projects about to be uploaded, including so Evan Smith, who works here and is actually a future graduate student at NWU, is he and Sophie Knudsen, who also works here, and Maureen Prestige built a horn antenna to look at the 21 centimeter line. So they're going to upload their plans to the website here soon. And actually, I've already written and posted a couple of blog posts about this antenna to the website. So it's already started and it's growing more. And we're hoping to gain more contributions. So if you have any ideas or would like to put it in light, please talk to us. So to summarize, and this is something that, this slide I think is probably something that's like really old news for everyone here. It's like stuff that you know without even thinking it. But I'm going to say it anyway because it was all new to me. So just to summarize what I've learned from this experience is that first of all, that patience and stubbornness are worth it. They do have they bring fruit, and so always stick to it. If it doesn't work the first time, it'll probably work the 10th time, maybe. So also I learned that doing a project like this is not as simple or streamlined as it seems from reading other people's descriptions or from books, because of course they've had to write it out in a format that makes sense, but if you actually write up your process, it's obviously full of like twists and turns and things that don't make sense. So another thing that I'd like to warn is that if a project is advertised as being for the absolute beginner and you have it done in 24 hours, that never ever works. So being an absolute beginner, I found this book, which is actually a great book, but it's a little bit outdated. And so the project said you could have this VLF antenna done in 24 hours tops. Well, I worked on this for several months and it is still being improved. So obviously take that with a grain of salt. And so to that, of course, if something works in theory, it doesn't necessarily mean it will work as well in practice. And that's just sort of common sense for a lot of you. It's, if the book says something may not be right, it could be outdated, it could be that it works in some ideal situation, like where temperature doesn't matter or something like that. But finally, probably the most important thing I learned is that the best way to learn about amateur radio astronomy, or really anything, is to just jump in, and most of all, to find people who are kind enough and willing enough and knowledgeable enough to share their experiences and explain things to you, which is what I was lucky enough to do. So I'd like to end on that note with a few thank yous, and I hope this was not too long a list, but I couldn't leave anybody off. So first of all, I'd like to thank Richard Prestige and Steve White, both of whom work here for basically walking me through this entire process. And so Steve built the circuit board and explained all the electronics to me, and Richard helped me understand the physics and the theory of electronics, as well as like testing procedures and stuff. And they just both, I couldn't have finished this project without them, so just a big thanks to them. Of course, I'd also like to say thanks to Sue Ann Heatherly, who invited me to give a couple of educational talks here about the antenna, and who's just been a big reporter for me as I've been here. I'd also like to say thanks to Evan Smith, who's helped out a lot with the Open Source Radio Telescope website and is doing a great project for horn antenna. Eve Hoff as well has provided some really good suggestions on electrical engineering, so thanks to her. I'd also like to say thanks to my family for providing moral support and putting up with my frustrations and providing some good suggestions when I was confused. So of course I'd also like to say thanks to the staff at the Green Bank Observatory, especially all the people here who have just been kind enough to talk with me about what they do and how they got where they are. And it's just been great to work with all of them, and I can't say thanks enough to them. And of course, thanks to all of you here for having me and for letting me talk. I really appreciate it, and I've enjoyed talking to many of you and hearing some of your talks. So, thanks. So, any questions?
Where are you going next?
So I just finished another presentation. They asked me exactly the same thing. In terms of college, I'm not sure yet. I hope to double major in electrical engineering and either astrophysics or physics. I want to eventually be a radio astronomer, and I'm especially interested in astrobiology. And to just kind of keep doing what I'm doing. I've done a lot of projects here. Last summer I worked on an RFI mitigation project. This summer I'm working on a GBT planning project, and I'm going to apply for some time on a 20-meter study neutral hydrogen around Andromeda. So I just kind of hope to keep this up and we'll see where I go. Yep.
What was the most difficult part of this project?
Most difficult. So I say probably the most difficult part was when I was trying to work out a book. I was super frustrated because the way the book described it, and you guys probably have heard of this method, but instead of using like an amplifier board or something for circuit board or like a super SID type thing, the book advised to use an audio cable to connect it to the antenna and connect it to my computer. And my computer's input didn't work that way, so I was trying to troubleshoot that. I was wrestling with Microsoft support people, and so that's probably the most infuriating part of the project.
Where do you live?
Huntington, West Virginia, so about 4 hours from here, 3.5. Somebody else? You good? All right, thank you.
So we have time for another impromptu presentation if anybody has anything in the back pocket. Bruce, do you think you have enough time between now and 5 to...
Sure, we'll go through it and
Okay,
don't finish it up. Talk to people in the lounge tonight.
great.
Okay.
Thank you.
Yeah, problem one. There's some place I plug my thumb drive in. Come here.
Sorry, I forgot to take mine out.
You see where you guys can turn power up. You all have it. That's okay.
Well, I had an opportunity to talk with Jay Lockwood. He's one of the scientists here. Is everyone familiar with great courses?
Okay, you come back to the space bar and move it.
Okay. He has done a great course on radio astronomy.
Back and get the space bar.
It will be available in the fourth quarter. So if you're interested in learning more about radio astronomy, it's 24 half-hour segments.
What's his name? What's his name?
Jay Lockman.
Is it just an introductory or just a little more in depth?
It's a little more, it's 12 hours, so it'll be a little more in depth, but I mean, it's not going to be, you know,
So when you say fourth quarter, you're talking about the end of this year?
October, December.
Okay.
Online?
The course is finished. It was done here. He has a white shirt and tie on. But
Is this online?
no, this is, you can download it, you pay money for it.
Yeah, you can do it online, but you have to buy it.
You have to buy it, yeah. I don't stay any place long enough to, I download it myself.
Audible.com has them too.
Okay, well, I'm going to talk about phase noise and its effects on radio astronomy receivers. Phase noise seems to be kind of a new buzzword you're seeing in receiver and transmitter specifications. And I had a discussion at a ham radio club meeting, and almost nobody knows what it is. I think this group may do a little better, but new buzzword for quality. It's basically a characteristic of an oscillator or a signal source. And putting it in simple terms, it's a measurement of short-term frequency inaccuracy. Okay, and for example, I'm going to take an FM receiver. My sketches were rather quickly drawn, as you can see, hand-drawn. But anyway, imagine an FM receiver working at 100.7 megahertz, and it's listening to Mozart or rock music or whatever somebody's listening to. And, okay, so you got your FM receiver, it's a mixer, 10.7 IF is typical, there's a filter to separate the channel, FM detector, and audio. And of course there's a local oscillator to do the conversion, and the 100.7 minus the 90 gives you 10.7 IF. Now we're going to muddy up the issue a little bit. This sketch is even a little cruder, but anyway, we have, on any oscillator, signal source, you'll have some small amount of FM noise. And here we're imagining, I took the oscillator that you can control frequency with a voltage, which is common in synthesizers, but I put a noise on the input of that. Then that noise will have both a frequency response associated with it and some amount of deviation. So it'll produce this FM signal, which is an undesired thing. Okay, one other point, the FM signal, but that's used for the local oscillator and the receiver. I guess you can imagine that if either the local oscillator or the input signal has FM modulation, it shows up on your audio. So that's basically the problem. So taking a look at what's in an oscillator. You have some kind of resonator, might be a quartz crystal, might be a surface acoustic wave, might be a capacitor, inductor, resonant cavity, but something that's a resonant circuit. Kind of like a high-speed version of a pendulum or something. But anyway, so you'll have a resonant circuit, and then it'll go to an amplifier. And the amplifier will have just enough amplification to make up for the loss of the resonant circuit and whatever is used on the output. So you have that, but the amplifier will have noise in it. Any amplifier will have noise. You'll have, because it's above absolute zero, the whole universe makes noise. So we have this resonator, any losses in it, resistive, are going to make noise. And all of these noises would result in both AM and FM components of the noise. Usually AM components aren't too serious in a receiver or transmitter or oscillator because they're usually limited. Someone to mixer with the FM components, or also called phase noise, are the evil guy. Just another way that you can look at an oscillator that I've seen, instead of taking and using feedback, if you just had a source of white noise, pure random white noise, and you ran it through a very narrow filter, and that, interesting enough, will mathematically give you exactly the same result as a normal oscillator. The advantage of that model is it really drives home the point that the oscillator always has noise in it. Okay. Now, because so many things in the world contain frequency synthesizers, we're going to take a little bit of a look at a frequency synthesizer. This is a fairly simple one. In this case, I've got 100 kilohertz reference that I chose. Some kind of phase frequency detection mechanism to make a correction on frequency. Some kind of filter, And of course, the real world, you've got noise source there being subbed into this control voltage, so that's going to add some noise to it. But the other thing we've got is a sample of that oscillator is run back, divided by 900 with a digital counter in this case, and that gives me 100 kilohertz there that's compared against 100 kilohertz reference, and that's used to correct the frequency. Well, a couple of things about that. First, the correction is only done every 10 microseconds. So in between the oscillator is free running, and whatever noise in it is making it wander. So that gives it a noise characteristic. So the characteristics of this VCO, the filter, and the phase frequency detector, and even random noise of the counters and stuff can make the frequency a little unstable. So again, the oscillator is just free running between samples. Okay, so what can go wrong? Thermal noise is a big thing, making noise in oscillators. Power supply noise, that's something that's easy to forget. If there's any noise on the power supply, it sends the oscillator wandering about and adds to it. Stray magnetic fields, you get a field from a power transformer, it cuts through the oscillator circuit, makes very small voltages in there that don't belong there. And next thing you know, you have some power line frequency, 60 hertz here showing up on your oscillators and FM modulation. Stray electric fields, brand of coffee and coffee cup nearby. The reason for that is that the guy that's troubleshooting the synthesizer is going through a lot of coffee, and the better brand will keep them alert better. Trying to keep a frequency synthesizer or any source of signal very low on FM noise or phase noise is very difficult. This is a reminder. You take a look, you end up with all the things to cure it. Next slide here. First thing you got to go is low noise power supply regulators. A regular old GP7805 is not the best thing to put on a precision oscillator or something. You get ferrite beads on all the power lines and control lines. I once heard somebody mention that when they're designing amplifiers, that you could take the gain bandwidth of all the amplifier modules in something and multiply by constant. I told you the amount of ferrite you need to make it stable. And there's probably a similar rule for synthesizers. I haven't figured it out yet. Feed-through capacitors on the control line, magnetic shielding, electrostatic shielding. So that says your synthesizer, which is done in a chip that weighs 5 grams, turns out to be 500 grams of bulk. Most of it being shielding and filtering and stuff like that to keep it working right. So for something that needs a clean oscillator, it involves a lot. That's why signal generators and things lots of times, my gosh, why does this thing weigh so much? It's transistorized. Well, it's all in the shielding. Now I'm going to talk about an example of a modern synthesizer here. I won't go through everything here, but it's an ADF 4351. We'll see in a few minutes why I just chose that one. Analog Devices was willing to let me reprint anything from the data sheet as long as I put that little note on the bottom. So that was a good start. And it's kind of interesting because it can be set from 35 to 4400 megahertz. That number may ring a bell with some people. There's a lot of gadgets that cover that frequency range. I'm pretty sure they use that. It's got fractional end synthesizer, which is an oddity itself, or a regular integer synthesizer like I showed in the last thing. Low phase noise VCO, that's an important part of it. On and on and on. It's basically a quite good synthesizer built in a chip there. I chose it for an example. And here's what's in it. It's looking at a typical high-end synthesizer now. First, you need a way to get all the setup data in because it's a digital device. Of course, got data registers and all that. The reference signal that comes in, well, you may not have the frequency available. You want to use the reference. So you can divide by just about anything with a 10-bit counter plus some extra dividers and multipliers and stuff on the reference. And then that's got a phase frequency detector there, which does it. Now this chip is interesting. It has a VCO on the chip that runs 2 to 4 gigahertz type of frequency range. And I'm truly amazed by the VCO because a few years ago, you would have had a cavity that took up a few cubic centimeters to make a VCO with the characters this one's got. It's got it all just hidden in the chip somewhere. Black magic and silicon, I guess. But anyway, they do have a quite good VCO on the chip. And then you've got your stuff for the phase lock loop process. Now divide by n and the fractional value, that's kind of an interesting thing because digital dividers divide by n, integer, and we want to divide by a fraction. The way the divide by fraction is done is going back and forth between two values. I think that may be better on my next, talking a little about fractional n. So basically, the digital divider is an integer device. So we flip back and forth between two values of n at some proportion of the time, we can loop it. That's going to add phase noise. You're telling the synthesizer to go to one frequency, now you're telling it to go to the other. You're telling it to go back and forth. So that inherently puts some FM in it. And it takes a bit to get reasonable performance on that. And there are several other synthesizer makers besides that analog devices, but anyway, they reduce that effect by, they use clever patterns of flipping back and forth. They don't just hold n for some period of time and then n+1 for some period of time, but it's flipped back and forth with a pseudo-random sequence. And that spreads the noise out and helps us. Use of a high reference frequency on the synthesizer helps, and that's why this thing, the VCO, runs at 3 gigahertz area. Okay, use of a narrow loop filter, that slows down the whole process, which that's a mixed blessing. And then of course a high VCO frequency with the digital divider helps a whole lot on making it a stable device. Okay, talk a little about phase noise on a graph. Notice the unit on this is phase noise in dB carrier per hertz. So that says if you have a filter with 1 hertz bandwidth and like a spectrum analyzer and tuned across this thing, and you got 10 kilohertz away, just the VCO by itself, there's a fixed voltage put on it rather than the control loop. So this is a character, so you got 80 dB below the carrier on that and 1 hertz bandwidth. Well, at 10 hertz bandwidth, you have 70 dB. 100 hertz and on up. So as you start looking at it with a wider bandwidth, the noise, of course, is more because it is per hertz. And with frequency, it drops off with range as you go away.
So that's kind of cheap.
Now, once you close the control loop on the synthesizer, it does a very different thing. If you took a look at this part of the curve right across here, that matches almost exactly to the curve that the synthesizer has when just the VCO is run without any control loop on, just with a stable DC voltage on it. In this area here, the FM noise or phase noise is all a lot lower, and the reason it's a lot lower is the control loop is continually correcting it here. And then this one has the things where if you want an output frequency of 3 gigahertz, you use divide by 1 on the output. If you want a frequency of 1.5 gigahertz, you divide by 2. Well, anytime you run through a digital divider, assuming the digital divider can have a lot of digital noise in it, you'll lower your noise by 6 dB, and that's why there's the advantage of running the VCO at a very high frequency, besides making the resonator smaller, and like I said, by some magic fitting on a chip. So you can see as the dividers run down, as the dividers are used a whole lot, you begin to see that it stops getting better out of this region. And that's because basically digital noise in the dividers, I mean, when you tell a flip-flop or in a counter to change, there is some randomness in when it actually changes, just due to thermal noise. Thermal noise is everywhere, like it or not. The universe is noisy. And that's the noise of that getting into that there, so it causes these to flip off there. But you can see that the noise gets quite low when you divide it down. So like this was used in an HF receiver or something like that. That would actually be quite good performance on that synthesizer. Okay, and then this is one of the reasons I chose this. If you go to this guy's website, KC4RI, and he gave a talk at Southeast VHF on that. He's got some examples of using an Arduino board to control the synthesizer. So it's a fairly easy programming device, and he has a program that you can download from his website and modify to your liking. And then you go on eBay. Remember, I think we heard about eBay earlier. It's where you buy anything odd, the odd marketplace. So $25 can get you a board with that chip mounted on it. And you take a look at that chip, it's got a solder pad that needs to be soldered in the middle of it, and pins all around the outside that are barely reachable. You could not solder it by hand. So you buy this little board that has a chip mounted down and you're good to go. And then, yeah, so anyway, that was another reason for choosing that particular chip as an example device. But why do we care about phase noise? Now that's a big thing. Actually, if you have a total power receiver, it really doesn't matter a whole lot if you have phase noise. It'll move the frequency around a little bit, but the noise on a normal total power receiver, something you'd be looking at with that, the spectrum is pretty flat. If your frequency moves a little bit, who cares? You get into a spectrometer, however, that frequency of your receiver local oscillator is jittering around, or if it's a digital receiver, the same problem applies to the sampling clock for the AD converter. It has exactly the same stability requirements as a local oscillator on a super heterodyne receiver. But it'll smear the lines between the bins. So if you were trying to do something like Zeeman effect, on a hydrogen line coming through a cloud to see what the magnetic fields were, well, you would have two spectrum lines spread apart by, fraction of a hertz kind of thing. And any smearing of the spectrum would mess it up. Or just normal hydrogen lines. Look, you really don't want the spectrum to smear the lines between the bins. So you need a low phase noise oscillator or sampling clock. Okay, and an interferometer, if you had a separate synthesizer on each receiver of the interferometer, used a common clock or something synchronized, well, the phase noise will reduce the correlation between the channels. So those are the areas where counts. Like I said, on a simple total power receiver, it probably wouldn't be too bad having a lot of phase noise unless it was severe enough that, well, one of the things with phase noise, it'll act almost like a second local oscillator on the receiver. So you're listening at 1420, the local FAA radar is running on 1310 megahertz, and if your local oscillator, your receiver has any phase noise out about 100 megahertz area, it'll take a radar pulse and reproduce it in your radio astronomy channel. So that is a place where it could get you on a total power receiver even if it was really bad. But anyways, that's the thing about it on phase. So I was going to there was another thing I threw in here on it while we were talking interferometer. Remember, I like interferometers. That's kind of my screwball addiction or something. But anyway, so we're going to take a couple of antennas and we're going to put them together and make an interferometer on it. Now, we're going to get the fringes from the Earth's rotation. So, okay, the Earth rotates. I could say that as it rotates, it moves one antenna closer and one nearer to the source by a slight bit. That's actually where the fringes come from. But it'd be easier, a lot less scribbly, if you assume one antenna stood still and the other one moved twice as much, and it would get, have the same effect there. Okay, and then I said, well, let's calculate the relative velocity of that little movement there. I took a look at antenna space. I just said 100 meters at 1400 megahertz to throw out a case. So 2 pi times 100 meters times 3600 seconds hour times 2400 a day. And that would turn up that I would have a velocity difference between the two antennas as far as the source is concerned of 0.007272 whatever meters a second. So that's a very small difference there. All right, now I'm going to take a look and see what would be the Doppler effect due to that small movement. And by the way, this Doppler formula is actually incorrect if you have anything moving at a significant velocity, but very low velocities, like even for like police radar, or for this case, it's fine. But if you get things near the speed of light, that formula falls apart. So it's simplified. Anyway, the delta frequency that we're going to get from that, we got 1420 megahertz. I'll put the power e to the 6th there, or power 10 to the 6th there. 300 there from 300 million meters a second that light travels, c, and the velocity we have there. So the delta frequency is only 0.34 hertz at 1400 megahertz. So that's kind of why it's so important to have the oscillators locked to a common source. If you could build an oscillator that had 0.001 hertz stability and put it in each receiver, you could have each receiver with its own local oscillator, and you can get away with it. You still get the fringes, and that can be sorted out. But this works out to be a time period for one cycle of the Doppler shift of 29.05 seconds. Well, I took the same case and I threw it into radioize for that, and said, well, I got a baseline of 100 meters, it's on the equator, so I don't have the complication of declination, which I assumed in the first case also. Wavelength, okay, I put in frequency, it drew the wavelength for me when I hit the calculate button. Declination, 0 degrees, and notice the same thing of, 29 seconds per fringe, so that's, pretty slow, but looking at it, a frequency drives home the frequency stability requirement, because I'm all the time hearing people that want to do an interferometer where the local oscillators are separate, and it just ain't going to work because you're looking at an effective frequency that's so small on that. So I did finish up with that. So look at it as a Doppler shift is another way. Never heard anybody look at it as a Doppler shift before, but if you go through the mathematics of it, it does produce the expected results. Okay, any questions?
If you have a common clock, or common oscillator with phase noise, does that?
Okay, so if you have a common clock running an interferometer, you got the two local oscillators or sampling clocks in the receiver that's digital. If they're run off of a common clock, then you'll have the phase noise will jitter it around a little bit and it'll smear your fringes so they won't be quite as intense. If the phase noise is small on them, if they're good synthesizers, like the one I use as an example, you probably get away with that pretty well. But if you have a synthesizer that was kind of noisy, you can smear it to the point where the fringes would almost go away. So that, because everybody's wanting to do long baseline interferometry. Everybody kind of thinks it's a neat thing to do. Well, NRAO does it with the hydrogen maser frequency standard each device, and hydrogen masers are twice the size of a washing machine, filled with electronics and thermostatic controls and other things. But interferometers are real touchy about that frequency. As soon as you get to the point where you can't cable between the two antennas, it's become very complicated. Okay, any other questions? Okay, thank you. One other comment, the paper on that will be appearing in the next SARA journal. It wasn't quite together in time to make it in the proceedings. Yes.
I think nobody else wants to.
Yeah, good.
You can?
What?
Right.
Ah, yes, we're right.
Yeah, we're speaking up
Okay, is everybody eager? Is there anybody that didn't get a ticket?
Radio Joe.
Ticket, who did not get a ticket?
Thanks.
If she bought, she's a member, she gets a ticket?
Even more fun.
Is Crowley gonna hold it up? Is Crowley gonna hold up the process? Easy, looks like that,
All together,
I think we were both told to lose weight. Unfortunately, that's a lawsuit that she can make, I can't.
All right, everybody has a ticket.
The whole stuff, up all this stuff. Tell me what.
Well, somebody needs to drop it so that we can say that.
I'll just do that, that's easy. You like to comment? Okay, ending 8:42. I want to check that.
Yes, check it.
No, that's 663 in the beginning.
See, mine's got 2 8s.
How can I pick him first?
I don't know.
This is weird.
You do have a 36.
Oh, by the way,
839.
you can grab as many of the connectors as you want.
839.
Gary?
This is rigged.
That's Gary.
861.
Bingo.
Oh, anybody or Jay?
Yeah, Jay.
Look at it.
I'm happy with that one. 864. 864. Ah, it's a student.
Yeah. Hey, student, you can take as many of the connectors as you want.
843. Eight five one. Thank you for trying. Here it is too. Eight four one. But I'm not going to call it. 874. 874.
I got that.
871. You were taking these up. Well, it can't be that it, but the first one.
Yeah, that was a fluke.
867.
I don't think you guys can do it.
897.
What's your,
897. Yep.
Who got the synthesizer?
That would be Gary. Gary.
Gary, what? You got this.
Oh, I had some more stuff to give you for it.
Really?
Oh, yeah. The software, we're working on the software.
Let's go, guys. This isn't difficult. You got a bunch of people that are anxious to get to the table.
Should get easier over time.
Good. 853. 853.
By the way, on the connectors over here, you don't.
You don't need to take it out. Yeah, you don't need to take it out. 894. You never say you called 198?
Yeah,
If you catch anybody cheating, you just take them and hang them from the great big telescope. 896. There's a painting up here you might be interested in.
Oh, yeah, I think I recognize this.
I drew the painting last year. I was given a 2-inch telescope, grass telescope with a beautiful mount. I think it sells for a couple $1,000. So anyway, that picture of the GBT is mounted right behind it. 860. 860. 860. Is that you? 881. 849. 849. Oh, we have a supervisor. 887. No, it's interesting, we haven't picked any of the spouses out of here. 852. Have the man from East Fishkill.
You're from Fishkill?
East Fishkill.
That's where IBM used to be. I taught a class there once. Oh, yes. Well, that's when I ran into the 90s from Fishkill.
Mrs. Soldiers, telephone. If you want to reflect it. 844.
On the connectors, take a couple of them.
844. Going once, 844. It's someone's spouse. 844. It's either yours or mine. Okay, go on. 866. It's just been waiting patiently. 862. Did I yell out 870 yet?
No.
Apparently not. Eight, 886. Eight, 7, 6.
Have a banana club.
Sorry about that, Ken. Here we go. 858. Eight, 6, 9. 8, 6, 9. 8, 6, 9. What number are you? I'll hold you next. What number are you? 850, is that you? Could it help? 850?
Sold what? Sold what? Sold.
I remember him. He was up there before. Don't worry about it. But I can't trust you. Who can I trust? The government? 848.
Hey, right here.
It took me a while to think of your number.
Let's see, this is going to be,
Part when you're done, stop looking at your number and call. I should have double checked.
What did number 1 do?
it's yours. Good, and squat.
You want?
Squat.
I got my nose. Yeah.
863.
I was gonna say, it's probably a little bit bigger than you said.
863. One more time, 863. Okay, 877. It's about time you got up there, Charles.
Thank you very much.
859.
You got it.
Congratulations, Thomas.
I need a new coffee mug.
Take two.
There's the word. Be careful, right?
868. What'd you get, Charles? 856. 878.
We got our tickets at the bottom of the barrel, I guess.
She's got to be last.
878. Eight four zero. 879. 879.
Taking color to connect to some of it.
883.
Oh.
884. 884.
What page on the synthesizer?
Yeah.
43.
Yeah.
884, one more time.
You know what, it's like,
854. 854. We'll let them know that we're looking at that. Eight, 2. 8, 2. 857. Way to go, Adrian.
That's right. It's perfect. We'll get a clog over here though.
Adrian, can you say that?
Okay. Bidding boards.
What are you looking for?
846. 846. 846. 875.
Okay.
845.
I don't have
880.
I'm really proud of
847.
847.
865. 865. One more time, 865. Oh, there we go. And last but not least, the one who answered the call, 855. 855. I saved the best for last. Anybody who wants whatever's left, come on up and grab it.
You gotta frame that.
Actually, have the U score was still there.
You got some more.
I wanted to get one more, but we call it a night. What I've learned, what's interesting is I'm seeing more and more couples coming to this and both helping. So this event for 2017, there was another person, that would be Gary and Carla, that I wanted to give an award to. And at first I gave it to Gary, I was going to put it in Gary's name, and then I thought I would call it the memory team. So Chip's going to take honor that one.
Side down. Oh, yeah.
But the thing is that I'm going to take this door prize home. I need a letter of authentication because I'm going to say I got this as a door prize. She's going to pull the BS flag on me because she's a hand operator. She knows what stuff costs.
I believe Ellie's wanting to, or did you have, what's next? This is Ellie's mom, the young lady who gave us the presentation.
Thank you. Thank you. My name's Dina White. I appreciate y'all giving me just a couple minutes. So, obviously you all know how near and dear this place is to your hearts. It's near and dear to our hearts since about 20 years ago, and my husband and I took a wrong turn out of Snowshoe and came down here by accident and fell in love with it. And now my daughter is, and my son also has done some work here, or a video for him, but we can't thank them enough. And last summer, it really came to a head when she got to do the work with Dr. Prestige and an undergraduate student from Oregon Tech. And then many of you are aware that the environmental impact statement is published, which is 5 options for how the NSF is going to decide their funding for the observatory. So because of that, we decided to form an advocacy group. It's called Go Green Bank Observatory, or Get Organized for Green Bank Observatory. And what we do, we have a Facebook page and a web page. During the 30-day public comment period last year, we provided fact sheets, contact information for legislators, different things to help make it easier for people to be active and advocate for this facility and tell them why it's so important to continue the funding. So We've kind of kept on going, we've still got things going on. The draft environmental impact statement will be coming out in the next couple of months. There'll be another public comment period where you can write letters to your legislators as well as to the NSF, and you can attend a public hearing that will be here on site to be determined yet. We'll be providing that information on the webpage. We got invited to a women's conference in technology in Charleston a couple weeks ago, so we put together this information. On one side, the fact sheets that you all are very familiar with about the observatory. On the other side, it's about our organization and what we're doing, and it has our webpage and stuff, so if you all would like to, I can pass these around, would you be interested? And that's really all I have. You like Okay, great, thank you. Thank you so much.
Make yourself useful.
We just need
Two more.
Well, this one's not as fast as
Yes, I was listening.
Okay, done? Done. Where are we at? Are we done?
Adjourn for dinner.
We're adjourned for dinner.
You got the handsome alien too. That's a good call.
You've ever heard of the
In your case, well, I would think, yeah, I had all
glasses? Bring them to the... Fine. Just came looking for them, thank you.
Yeah.
As soon as I hit the door, I knew I didn't have them.